All right, guys, I want to get into some more examples of what we were doing yesterday. But before we get there, I think it's important to understand if you're a Desmos person, in TI 8384, you have to type it in this way that I'm going to demonstrate. But Desmos understands that cosine squared x, when I write it this way, that what it really wants, or what it really means, is this. Cosine of x, the whole thing squared. Okay, can you see if the graphs are identical, right? So Desmos knows that when it sees this, to actually convert it behind the scenes into that. Okay, but when it sees this, it gets confused. Okay, it is not programmed for you to use higher degrees than 2 right there. So if you have the interest in graphing cosine cubed, fourth, fifth, whatever, that you have to type in as the quantity cosine of x raised to the third, like that. Okay. Now, I don't know if I go cosine x and raise it to the third that way. Okay, so that is okay. I don't necessarily need the exponent, or the parentheses. I would just be cautious of that. Because if I do it that way, and because it does know how to do things or address things without the parentheses around the argument, and if I do that, now I'm looking at that red function instead of the blue one. Okay, does that kind of make sense, everybody? So just understand that notation. And the reason I'm talking about that is because one of the problems today that we start off with is this. It says cosine of x plus cosine, I believe it's cubed. Oh, no, it's cosine cubed x. So cosine cubed x, so because it's cubed, I have to type it in this way. Plus then sine squared, which I can type in that way, is fine, times cosine x. I graph that. Okay, let's see what it's saying. It doesn't understand. Use parentheses around the argument of sine. Okay, so when I didn't put parentheses around this here, it doesn't know whether I should have parentheses around the x or around that. Does that make sense? Because that graph there, because of what's in the arguments, is completely different than if I would have meant to put parentheses there and left them out there. Does that make sense? Okay. So just make sure that you understand the location of parentheses changes things dramatically. Okay. Kind of a weird curve there. Okay. So that's the one we're looking at. Okay. And we want to simplify that. Okay. Well, if I look at that graph, what does that graph look eerily similar to? Cosine. And if I look at the ordered pairs, 0, 1, pi over 2, 0, pi negative 1, 3 pi over 2, 0, 2 pi 1. That is exactly cosine. Okay? So what we want to do today, and if I type in cosine, is see, well, that's stupid, that kept the same color. What we want to do is, can we see algebraically or analytically why this simplifies down to that? Okay. I like to sometimes you can do that, sometimes you can't, because sometimes these aren't going to just break down just to, cosine x. Sometimes they might break down to, I think one we get to today goes like negative cotangent of x. You might not know right off the top of your head what negative cotangent of x looks like. Okay. And to make the argument of what we started with and what we get to, should be, like I said, something kind of odd like negative cotangent of x. But with this one, I now know, and the reason I do this, or I may talk about this, is because now I know when I should stop simplifying, right? Does that make sense? Okay. If we talk about simplifying, if I take 12/6 and I tell you to simplify it, and you write it as 6/3, did you indeed simplify it? Is 6/3 simpler than 12/6? Yeah. Okay. But did you simplify it fully? No. Okay. Should go down to 2, right? That's fully simplified. All right. But our degree of simplification, we might not be in agreement on those things, okay? And so when I ask you to simplify this, some people won't go as far as they need to, okay? And usually when somebody doesn't go as far as they need to with simplification, two things are the reason for that. Either they're not fully skilled in their algebra, or they're not fully informed on their identities, okay? Or a combination of both. There will be a series of problems towards the end today that kind of fix that, okay, or eliminate that for us. You guys remember doing proofs in geometry? When we did a proof in geometry, did we ever know how many steps were going to be in that proof? Not really, right? Okay. But if we had a given and then we had a prove statement, wasn't this thing always the last thing in our two-column proof? Okay, that always showed up right there as the last statement, and then we had to come up with a reason over here, right? And that told us we were done, right? Okay, we will have some questions here in a little bit that actually do that, okay? Which will be, it'll look something like this eventually, okay? So they'll say, take this thing here, simplify it to a point in which you generate that, and then you know you're done, okay? But if they don't do that, usually the issue is that people don't go far enough, okay? So just be careful with that as we work through homework questions. WebAssign, I think, will tell you, yes, you have an equivalent format, but it's not fully simplified or something like that, okay? So when we go through these problems, I said yesterday that the number one thing you're going to look for is if there's powers bigger than 1. So you're looking for things that are squared, cubed, raised to the 4th, raised to the 5th, whatever, okay? Because when that happens, you can start using identities. That's going to be a nice thing. And you might be able to use an identity right away, right off the bat here. We'll see. Maybe do this one or two different ways. But usually, if they're all powers of 2, you're probably going to substitute right away. If there are powers that are greater than 2, you're going to start factoring, okay? And if you remember back to college algebra, I don't know if I still got it written somewhere. Probably not. Somewhere I'd written a list of factoring techniques that we use as kind of a hierarchy in order to factor, okay? Same thing here, okay? If we just said that we are going to start factoring this thing, okay, then we go through our hierarchy of factoring. If you remember, that hierarchy started with like a GCF. That was always the first thing. Does a GCF exist? The next thing was, can I use like a product sum technique? Okay. Maybe we could use the AC method. Maybe we could use the quadratic formula. Okay. Maybe it was in quadratic form. Maybe it was the rational root theorem, P over Q. You remember seeing something like that? Okay. Same idea happens here. Okay. Now, some of these things are going to be a little bit more difficult to do than others. Okay. Like P over Q would be kind of a complex thing to do with some of this stuff. But our GCF, that's the first thing I want to look at all the time. Okay. And when I look at these terms, there are two terms. There's that term and that one. Okay. Do they share a GCF? Cosine X. Okay. So I'm going to factor that out. Now realize when we factor it out, because this is not an equation, but that factor has to remain. Does that make sense? Okay. If we saw something like this in college algebra, which would have been like 2x squared plus 6x plus 8 equals 0, we would factor a 2 out, right, on the left-hand side? And then a lot of times we let that 2 just disappear, because what we'd be really doing is dividing the left-hand side by 2 and dividing the right-hand side by 2, right? So it disappears. Here, because it's not an equation, it's an expression, you can't let it disappear, because what is left over here, or what I generate here, this new format, should still produce the same thing that that produces. Okay? So now, factoring out, what's that operation? The same as what? Dividing. So if I factor out cosine of x out of this, it was cosine cubed divided by cosine to the first. What's that leave you with? Cosine squared. And if I divide the yellow thing by cosine x, that's going to leave you with just sine squared. And we have the identity that cosine squared plus sine squared, that's the Pythagorean identity, that's the main Pythagorean identity, which is 1. And you're just left with cosine x. Good. Okay. So here's my question, and this is, a lot of technology is coded with sine, cosine expressions. Okay. If I'm for whatever maybe program, application, GPS, or whatever it may be that is taking this cosine cubed x plus sine squared x cosine x formula and doing something, evaluating at different angle measurements of x, there it has to input 3 things, right? It has to input it for the cosine cubed, it has to input for the x, or the sine squared, and it has to input it for the cosine. So 3 inputs, okay? So let's talk about let's say that x is 60 degrees, okay? So then I've got cosine of 60 degrees cubed plus then sine of 60 degrees squared times cosine of 60 degrees. Does that make sense? What's cosine of 60? Should be 1/2, right? Okay. What's the sine of 60? Oh, should be a plus sign. Radical 3/2. What's the cosine of 60? 1/2. Okay. So now to evaluate this, so I had to do those 3 substitutions. Now to evaluate, I'm going to have to go 1/8 plus then 3/4 times 1/2, right? And now it's going to have to do that algebra. So I have 1/8 plus 3/8, and now it's got to do that algebra, gives me 4/8, and then it's got to run through and say, okay, are there common factors? And there are. It'll give me 1/2, right? Is it much easier? Yeah, they're going to just say, what's the cosine of 60 right there? It's 1/2, right? Does that make sense? Okay. Because the idea then is, okay, maybe we could do that. And you might be saying, well, that's trivial, Mr. Fay. It was 6. I could do all that work down there when we put 60 in. And then my next question, okay, do it with 30. And my next question is do it with 45. And then do it with 120. And then 135. And 150. And 180. Okay? So you have to go through all of that algebra over and over and over and over again, right? Wouldn't it be so much easier to do that algebra one time with what we've got highlighted up there, okay, with generic values, get it simpler, and then use that thing to generate those or to evaluate at different angles over and over and over again. Okay, so that's kind of the purpose of what we're doing here. And that in itself is exactly what is happening or what we're checking when we do this. When we graph the original and say, okay, when I graph that, do they give the same output? And they do. Okay. So that's a situation. And what I'm trying to do here, guys, is we're not going to see, and I told you this yesterday, enough questions that you become experts at this. Okay. I would argue that there are questions, and we might even come across some as we work through these examples, and then more examples I pull from our textbooks. There are questions that throw me for a loop, and I have to sit there and think, okay, I did this, what do I got to do next? Okay, so I've been doing this for 20 years, and there are still things that I'm not going to be able to zoom right through them. Does that make sense? Okay, so to get really good at this stuff, we're not going to see enough in class. All right, so what I'm going to try to do, though, is show you enough varieties, okay, so that we don't get to something on a quiz or a test or final, or we get to calculus, and we have to do this because in calculus what we're going to ask is, what is the derivative of this thing? Or what is the integral of this thing? Okay? Which would be, what is the, we might ask something like this, what is the integral from, let's just say, 0 to pi of that thing? Okay? Which means find the, if you were to graph this, find the area between 0 and pi and the x-axis. Okay? So that'll be a process in calculus. But to do that, it is much easier to simplify this first and then find the integral of that simplified version. Okay? But the more varieties I think we see, I don't want to see just, ones like this where there's always a common factor and we do, 80 of these in class that have a common factor at GCF. And then you come across one of these and not have a clue how to do it because we've never seen one like it. So I'm trying to give you as many varieties as I can that explore or use as many different algebraic principles as possible. Okay. So this one says simplify sine theta minus cosecant theta over cosine theta. Okay. No powers here, right? No powers greater than 1. So what would you think the first step to be? Okay, so I'm going to address the objects that are not sine and cosine and put them into sine and cosine. So cosecant is 1 over sine. Okay. Now I'm going to draw, I think it was useful in the last class. I think it made things make sense to them a little bit on maybe a different level. Let's say, so that we're doing this for theta being, just like we did in the last one, we let theta be 60, but let's let theta be 30 here. If theta were 30, what would this number right here be? Careful. It'd be 1/2. Okay. And if this was 30, this would be minus 1 over 1/2, right? And then this one would be the radical 3 over 2. Okay. So because these were general or generic values of theta up here, they said simplify. If I gave you a specific value of theta, they would say you would substitute this and say evaluate, right? Okay. And really the only thing that is different is when I say simplify, it's saying come up with the most concise, simplistic expression. Here it's saying come up with the most concise, simplistic value. Okay. The division bar is a grouping bar. Okay, a grouping symbol. So it tells me to do that first, and then to do that second. Get them into one value, right? Okay. This green thing should turn into one number. That's basically what the grouping symbol is supposed to do, right? Order of operations, PEMDAS. This would effectively have parentheses now around the numerator. If I wanted to do that, what would be the first thing you do here? Common denominator. You would probably change. I would think you'd probably change this value to 2 first. And now if I want to go 1/2 minus 2, in order to actually do that, I need a common denominator of 2, right? So you write this as 1/2 minus 4/2 all over radical 3 over 2, right? So let's do that with this. Okay, because that's what this is saying, right? This is saying 1/2, that number right there, minus 2, that number right there, right? And we said we need a common denominator. So what would my common denominator be up here? Sine theta. So what I always like to do, I don't like to do a lot of this stuff in my head, because when I do make a mistake, if I've got more steps written down, I can go back and identify where the mistake started. Does that make sense? I can figure out the place that I messed up, and I can just erase up to that and continue then again through the problem. Okay, so if I do that, so if I make this, so this term right here is going to become this one. If that was a 1 right there, what did I multiply that 1 by to get the sine theta? Sine theta, right? So what do I need to multiply the numerator by? Sine theta. So then when I multiply sine theta by sine theta, sine squared theta. Good. What did you have to multiply this denominator here by to get that? Nothing. So this stays as 1, right? And then cosine theta. Okay. Now let's draw back the comparison to the specific value question. Once you had those as a common denominator, what could you then do? You actually do the subtraction, right? And a lot of us would probably just go 1 minus 4 and get negative 3, but it's this. You go 1 minus 4 over 2 all over root 3 over 2, right? Can I do that same thing here? Okay, so we'll take that numerator, and it's going to become sine squared theta minus 1 over sine theta, right? All over cosine theta, okay? Now let's go back to this. You know that 1 minus 4 is what? Negative 3, correct? Okay. Now, that negative 3 is an identity. Is that always true? Okay. You made a substitution, did you not? Same thing up here. There should be a substitution for this. There should be something else that we can replace here. Yeah. So when I look at that, when I see sine squared and a 1, whether it's added or subtracted, that's just going to hopefully elicit this. It's going to help me remember the sine squared plus cosine squared equals 1 identity. And now I can augment that. I can mess that around a little bit. I can take that number and put it over there, and that number and put it over here. And will that give me sine squared theta minus 1 equals negative cosine squared theta? Okay. So this numerator right here, let me... So this thing right here is going to become negative cosine squared theta all over sine theta all over cosine theta. Okay. Go back to this one. Once you have one fraction divided by another fraction, how do you evaluate that? Multiply by the reciprocal of that thing right there, right? Come back here. What's the reciprocal of this thing right here? Okay, you're right, but we don't want to reintroduce secant and cosecant. So it'll be 1 over cosine. It cancels out there, right? And then you multiply. So now if I multiply straight across, I get negative cosine squared theta over sine theta cosine theta, right? Okay. What's going to happen with the cosines? That one, because there's 2 of them up here, right, being multiplied together? So that cosine of the first is going to cancel with one of these, leaving me just negative cosine theta up top. And what am I left with on the bottom? Sine theta. Okay. Now what's cosine divided by sine? Careful. It's cotangent. Okay. Sine over cosine is tangent. So this is the reciprocal. And now I get that negative there. But my hope is, so that's a lot simpler than what we started with, right? We started with this ugly thing, right? Okay. But the hope is that you can see a comparison to what we would actually do with algebraic values, right? And here's my thing. Here's my thought. If I get stuck on one of these things, my hope is that now after going through chapter 5 and chapter 6, that we can kind of do what we did there in the purple. If I'm not sure what to do, let's choose theta to be 30 or choose theta to be 60. And actually evaluate the entire problem, the entire original problem with that and just get values. And say, okay, now if I wanted to merge this, I want to get this down to one value, I want to evaluate this. What are the algebraic steps that I would take? Because then those algebraic steps parallel 1-to-1 with the algebraic steps that you would take when you simplify using the general trigonometric functions. Does that make sense? Okay. Always be thinking about the notion that this here is just a number. That is just a number. That is just a number. Every one of these trigonometric identities or values, trigonometric expressions or whatever you want to call them, let's call this an expression, a trigonometric expression right here. It is a value when you know what x is. This is a numerical value when you know what x is. This is a numerical value when you know what x is. Okay? If you use that approach or use that connection, it could help you mightily with some of these problems. Questions so far? Okay, that's one where at the beginning of class I said was going to show up, and it doesn't maybe make a whole lot of sense to maybe look at like sine of x minus cosecant of x divided by cosine of x, and to look at that, and if I look at that, you might not realize that that's the cotangent reflected over the x-axis. Okay, it might give you an idea though. Hey, somehow I'm probably going to get tangent or cotangent to show up in my answer. Does that make sense? Okay, but it's not as kind of informative by looking at the graph here that we got when we did like cosine of x cubed plus sine of x squared times cosine of x. That's so much easier to see. Well, that's probably the cosine that's generated there. Okay, but looking at that one and then typing in my answer, negative cotangent of x, you can see that they are the same function. All right? Make sure you guys stop me or ask questions if some of them make sense. Those are the types of questions that ask you to simplify. Okay? I think these questions, the structure of the organization is a little bit different, but these are I like them better. They're more friendly to students because you know where you're supposed to get to. You know what the end result should be, and it tells you when you're done. Okay? As we go through all of these up here that we just did, okay? Somebody could have stopped there and said, I've simplified it. Okay? Now it's not fully simplified, so that's the issue. But you might get stuck because you don't know where you're going. Does that make sense? Okay. When we look at trigonometric proofs, identity proofs, we know where we're going. Okay. And here are some guidelines for these types of questions, and we'll run through at least one of these before we get out of here today. So guidelines. There's going to be two sides. It's going to be an equation. It's an identity. And they're going to say, prove that this identity is true. Okay? What you end up doing for about 95% of these is you're going to look at the two sides, and you'll be able to distinguish whether one side is more difficult than the other. Okay? One side is more complex than the other. Okay? You're going to choose that side. You're going to start with that side. Okay? And you're going to try to transform that side. You're going to employ your algebra skills. You're going to employ your identity substitutions, and you're going to manipulate through that complex side. Okay? Once you manipulate through that complex side using the correct identities and the correct algebra, that side should, at some juncture, turn into the side that you did not touch. Does that make sense? So you can show that you manipulate one side to become the other side, and that then is the proof that you have confirmed the identity. Okay? About 5% of these, you're going to choose a side, and a lot of times when you choose, and this 5%, it's going to be a flip of a coin which side is more difficult. Okay? There might be arguments for both sides. So sometimes you'll choose one side, start manipulating it, and maybe you get stuck or confused and say, I can't get to what they're asking me for. So take the other side and start manipulating it. And maybe at some point on manipulating the right-hand side, it shows up a line that you had created when you manipulated the left-hand side. Does that make sense? And then those two things would be equal. So then that would tell us that the top two things that we started with were equal. Okay, so we'll see if we can find a couple examples where that might take place. But like I said, most of the time, you're going to choose the most complex side. Use your known identities. Use your algebra. Use your factoring. Use common denominators. I always talk about it as do what the algebra tells you. Does it tell you to factor? Does it tell you to distribute? Does it tell you to find a common denominator? Does it tell you to divide a fraction by a fraction? Okay, use that knowledge. And if you ever get stuck or you're uncertain about identities, change things to sine and cosine, and that hopefully will get you unstuck. Generally, though, when you change things to sine and cosine, it's going to make you're going to make you rely solely on algebra and not on identities. Does that make sense? Okay, so it puts more importance on your algebra skills. All right, so this is our first example here. I'm not going to confirm this graphically. I don't want to do that. You would graph the left-hand side, graph the right-hand side, see that they coincide, and that would be the graphical proof. Okay. I'm going to move this over to give myself a little bit of room. Oops. All right, so you're going to decide what side is more complex. Which side here is more complex to you? The left-hand side, right? Okay. So what we're going to do is we're going to write down there's really not one mandatory procedure that you have to go through here in regards to your notation and your organization. I'm going to try to model for you what I think is the most appropriate, what is the most friendliest for somebody that's looking at your work, that's grading your work, to follow your thought pattern. Okay, when we do these on a final or a chapter test, unit test, if I can't follow your work, your progression, your line of thought, then I can't give you credit. Does that make sense? So if you've got work all over the page and there's no progression through there that I can easily follow, then it looks to me like you're just throwing stuff up there that might be true facts, but I can't put that puzzle together. Does that make sense? So what I think is good to do is say, okay, what side we're going to choose? We're going to choose the left-hand side. So we write LHS, which is the left-hand side, right? And we write that what it is equal to. It is equal to cosine of theta secant theta minus cosine theta. Okay? And now we are going to start working our algebra. Okay? Or working our substitution. So and I think there's two routes you can go here, depending on your level of knowledge, your depth of knowledge. You can maybe do this in 2 or 3 steps, or maybe you can do it in 4 or 5 steps. Okay? What do you think we should do first? Jimmy? Okay, change the secant to 1 over cosine. That's following it directly what I've kind of hopefully instilled in you the last day and a half. Okay? Now that we've done that, there's no other substitutions to make, right? There's no other reciprocal identities. There's no Pythagorean identities or anything like that. So what does the algebra then tell me to do? Distribute. Okay? And remember, this is a number, unknown number, and then you got a number minus an unknown number. Okay? So we got a quantity here with the quantity outside of the product. We can distribute. Okay? What's that going to give me right there when I distribute? It's going to give me 1. Okay? Give me cosine over cosine, right? So that's 1. And what's that going to give me? negative cosine squared. Okay. Now, if you're a person that understands your identities well enough and saw right here cosine and secant, because so you could have, I guess the steps are kind of independent here. I could have distributed right away. What's cosine times secant? 1, because you know cosine and secant are reciprocals, and if I go off the definition of a reciprocal, their product should be 1. So I could do it that way. I think this is more deliberate, more obvious, especially if I'm using this in my notes to, explain to myself. The purpose of my notes is so 2 weeks, 3 weeks from now, go back and revisit this stuff, reteach myself some of this stuff. The more that I have written, the easier it will be to reteach myself, right? Okay, so now we've got a cosine squared and a 1. Hopefully that reminds us of that thing, right? How can I manipulate this so that it turns into this? Yep, subtract that from both sides, right? So if I subtract that from both sides, it gives me exactly this, which would be equal to sine squared theta. Which, if it's equal to sine squared theta, that is your right-hand side, right? Okay. So I always start with listing the side that I'm starting with, left-hand side, and I can go through this progression here, and eventually the right-hand side, if I've done everything correctly, the right-hand side will appear. And once it appears, I just say, hey, I'm done. This equals the right-hand side. Confirm. Done. Okay. You might see, if you were to go through my videos or go through just YouTube in general, or I like to get on Google. I don't like to do this. It's not like I'm sitting at home on Saturday night doing this. But if I'm practicing this stuff for whatever reason, I like to Google, Trig identity PDF, okay, or Trig identity examples PDF, and you will see example after example after example worked out, and they use this kind of structure, okay. But at the end of it, they'll do this. They'll put a box, and they'll color it in, okay, or they'll write this phrase, Q.E.D, okay, which if we, wrong letter, it's Latin, and it stands for, don't know Latin, and I'm not even going to try to say this, but that kind of looks like demonstrate, right? Okay, so it translates that which was to be demonstrated, or what we were asked to do, we have shown. Does that make sense? Or we have proven what we were set out to prove. So if you ever see QED as an abbreviation at the end, you might see that. That tombstone thing, sometimes called a halmus. That symbol right there, you might see at the end of a proof, and that's named. It might be called halmuses. I think maybe it's after a guy's name. Like he started using it in the halmus finality symbol. Okay, sometimes called halmus's tombstone. It just means we're done. Okay, so those are things that, like, if you are a math person, you're really geeked up about math, and you're going to go on to college and take math. You'll have professors that use that stuff, and you have absolutely no idea what it means. They don't explain it; they just do it. It means you're done. Okay? You've set out to do, you've proven what you were set out to prove. So we start with the most complex because it's most obvious to apply the algebra that is present here. It's most obvious to distribute here. Okay, would you guys agree that distributing is easier than factoring? Yeah. You could have started with this side. Okay? But it's going to be very difficult for you to start with that side and ultimately factor it backwards to generate this at some juncture. Does that make sense? So that's the reason why we start with the most complex side, is because the algebra then is more obvious as we move to simplify. Okay. There will be problems. I look at these. Okay. Which one of those? If we look at this example 6, and we'll do these tomorrow. We're not going to have time today. Look at that example up top. Which side to you looks more complex? It's kind of a toss-up, right? Okay. And I think there's enough substitutions there that we could do either side. Okay. Maybe we'll do that tomorrow. I like to start the left-hand side there. I think fractions are more complex than things that are not fractions. If I look at the bottom one, again, there's a toss-up there, right? Okay, I'm not sure which one's more complex there. Maybe I just choose the left-hand side. Or maybe I choose the left-hand side and start working it and get to a point that I don't know where to go anymore, so I got to take the right-hand side, start working it. And hopefully, somewhere in my work, the left-hand side matched the right-hand side, and then I can say that they're the same. Sam? Yep, all same thing. Yep, and that's the thing that stinks with WebAssign when these pop up, because I just get in a habit of always using like theta or t or x. They'll use like u, or they want, if they use theta, you can't put x in. Does that make sense? And a lot of times, I'm really bad at it. A lot of times I just leave the argument off. It's terrible. You shouldn't do that. But I'll just like all right, like cosine over 1 minus sine equals secant plus tangent. It's very, very bad to do that, but I know that I do it, so I can address it anyways. No new homework.